From the ground, a thunderstorm appears as a chaotic mass of wind and rain. But viewed from orbit via infrared satellite, it reveals itself as a highly structured, self-contained thermal system. The deepest convective cells within these systems routinely punch straight through the tropopause, pushing their summits to altitudes exceeding 50,000 feet. Reaching the stratosphere requires sustained vertical velocity. Inside the core, continuous columns of air accelerate upward at rates exceeding 6,000 feet per minute. These violent metrics are governed by exact rules. The massive vertical development and the anvil-shaped top spreading out in the upper atmosphere are visible manifestations of strict thermodynamic laws. To navigate these hazards safely, pilots must deconstruct the mechanical life cycle of the cumulonimbus cell, tracking its evolution from invisible adiabatic expansion all the way to its terminal destructive downbursts. This entire engine requires three distinct ingredients to start: deep atmospheric instability, a high moisture content, and a convective lifting trigger. Because these three variables interact according to known physical rules, the exact altitude and severity of a storm can be calculated before a cloud even forms. The cycle begins with a starting condition at ground level. A parcel of warm, moist air is forced upward by a convective trigger, such as intense heating of the surface below it. This diagram plots altitude on the vertical axis against temperature on the horizontal. As the surface air parcel is forced higher into decreasing atmospheric pressure, it expands and cools adiabatically. Because this rising air does not yet contain liquid water, we apply the dry adiabatic lapse rate. This unsaturated air cools at a constant rate of exactly 3 degrees Celsius for every 1,000 feet gained. To find out when a cloud will actually form, we introduce the second variable, the dew point temperature. This is the thermal threshold where our rising air parcel becomes 100% saturated with water vapor. The dew point itself decreases as the parcel rises, but at a slower rate of 0.5 degree Celsius per 1,000 feet. This creates a net closure rate of 2.5 degrees between the air temperature and the dew point. The exact altitude where these two values intersect dictates the absolute theoretical base of the cloud. At that intersection, the air reaches 100% relative humidity. The invisible water vapor it carries suddenly condenses into a dense cluster of liquid droplets suspended in midair. The cloud base represents the exact mathematical altitude where adiabatic expansion forces a specific parcel of air into complete saturation. This saturation marks the beginning of the cumulus stage. During this phase, the system is characterized by continuous, warm updrafts that draw ambient air into the cell from all horizontal levels. A critical thermodynamic energy transfer occurs right at this boundary layer. By changing from a higher energy vapor state into a lower energy liquid state, the condensing water releases latent heat. This newly released thermal energy immediately counters the cooling effect of expansion, altering the mathematical cooling rate of the rising air column. Inside the cloud, we switch to the saturated adiabatic lapse rate. Driven by latent heat, the saturated air cools at approximately 1.5 degrees Celsius per 1,000 feet. This is exactly half the cooling rate of dry air. To understand the threat level, we evaluate this internal temperature against the environmental lapse rate, which measures the ambient, static air sitting outside the cloud. Because our saturated parcel is cooling much slower than the surrounding atmosphere, it retains its heat. It remains warmer, less dense, and highly buoyant compared to the environment around it. This sustained buoyancy acts as a vertical accelerator. It drives the cloud to build upward at a velocity that an airplane often cannot outclimb. Latent heat acts as the primary fuel of the storm. It turns what would otherwise be a self-limiting column of rising air into a runaway, unstable thermal engine. The engine reaches its climax, the mature stage, the moment water droplets or hailstones become too massive for the updrafts to support. Gravity wins, and precipitation begins to fall toward the surface. As millions of heavy drops plummet through the cloud, they drag the surrounding air down with them. This friction creates intense, cool downdrafts that flow directly adjacent to the massive, warm updrafts. Within the confined space of the cell, these opposing vertical currents shear against each other at high velocity. Penetrating this boundary exposes an airframe to severe turbulence capable of inducing immediate structural failure. Higher up, those vertical updrafts carry liquid water droplets well above the freezing level. They remain in a supercooled state until they strike a cold surface, like an aircraft wing, where they freeze instantly, destroying aerodynamic lift. The most acute danger often lies outside the cloud, if precipitation falls from the base but encounters very dry air near the ground. We observe a phenomenon known as virga. Here, the thermodynamic engine runs in reverse. As the rain evaporates back into invisible vapor, the phase change absorbs massive amounts of latent heat directly from the surrounding air. This intense evaporative cooling generates a localized parcel of dense, cold air. Stripped of its thermal energy, the heavy air plummets earthward. When it strikes the surface, the column violently deflects horizontally. This specific localized event is called a microburst. It produces an extreme, concentrated wind shear hazard that can strip a low-flying aircraft of its airspeed and push it into the ground on final approach. While the storm's updraft is formidable, the invisible downdraft triggered by evaporating rain remains the system's most lethal hazard to aviators. The thermodynamic engine cannot sustain this intensity forever. The heavy precipitation and cold downdrafts of the mature stage ultimately engineer the storm's own destruction. As the continuous output of cool air hits the surface and spreads out, it undercuts and blocks the warm surface air from rising into the cell, washing out the updrafts. Without that intake of warm, moist air from below, the cloud loses its vital vapor supply. The latent heat fuel is completely cut off. This initiates the dissipating stage. The system is now dominated entirely by cold downdrafts. The towering cumulonimbus structure begins to collapse, flattening into stable layers of stratiform cloud. A thunderstorm is a self-terminating system. It burns through its local atmospheric fuel until thermal equilibrium is completely restored to the environment. Pilots quantify instability before takeoff using the lifted index. It calculates lifting a surface parcel to the 500 millibar altitude. The index compares that lifted parcel's adiabatically cooled temperature against the actual recorded ambient temperature at that same level. If the calculation results in a negative integer, the lifted parcel remains warmer than its environment. That negative index definitively proves the air will continue to rise, confirming deep atmospheric instability and high potential for severe cumulonimbus development. Extreme weather is governed by precise mechanics. By actively mastering the invisible thermodynamic math of adiabatic expansion and latent heat, professional aviators shift from merely reacting to extreme weather to precisely predicting its most fatal hazards.